Hello everyone, welcome back to one more question from Organic. This question is about isomerism of some compound given. That structural formula of the compound is given and we are asked to calculate the different number of isomers in some of the categories. This question is from Ellen score test 3 and this exam was conducted on 27th May 2023. This question is from paper number 1. This was under integer based question. Here we go. So this question is that C4H6O will be having X open chain carbonyl compounds, Y unsaturated alcohols, and Z ethers. Out of these Z ethers, what we are having, Z1 are aliphatic and Z2 are alicyclic ones. We had to find 100x plus 10y plus z minus 0.1 z1 minus z2, something like that. So what is our strategy? How do we go ahead? What algorithm we should follow? That we'll be seeing in a moment. So we'll be seeing that this question has got some of the structural isomer, then we can be counting that for the possible stereoisomers. And actually this question, it was not very much clearly defined whether we should be counting only structural or stereoisomers as well. So there was some point of confusion. And actually when it is asked about the stereoisomer, they usually define the number of all possible isomers. Then we should be counting stereoisomers as well. Here there was some element of confusion because nothing was defined with respect to that. So if you talk about only structural isomer, we'll figure it out that the value of Z was 3 because only 3 carbonyl compounds are possible and unsaturated alcohols are found to be 8, while the number of alcohols was found to be, number of ethers was found to be 11, out of which 4 were aliphatic ones and 7 were the alicyclic ones where there was a cyclic ring present as well. So if we put this information of X, Y, Z and Z1, Z2, we'll be getting our answer as 391.3. Okay. When we are going for the possibility of stereoisomers, then the carbonyl compounds, that 3X was 3, none of them are going to have the optical isomerism or symmetrical isomerism possible. Out of the compound number Y, where we are having unsaturated alcohols, there are possibilities of the cis introns, we can be saying E and Z, as well as dextro-levo, which we'll be writing as R and S, possibly because if there are chiral carbons present, we do expect that this is going to have some stereoisomers as well, that is optical isomers basically. And in the Z, which was ether, again, same possibility arises. We can be having cis introns as well as we can be having chiral carbons, so we can be having both the symmetrical as well as optical isomers possible. So first of all, in this question, we'll be seeing what algorithm we will be following and how we can get to the actual number whenever we are asked such a type of question. So this algorithm, what we are supposed to be following, where we may not be missing any of the possibility or we may not be repeating any one of these. So first of all, we'll be deciding the degree of unsaturation for the compound given. For C4H6O, our compound what was given to us in this question, degree of unsaturation turns out to be 1. Because we are comparing it with the saturated hydrocarbon and we are going to we are ignoring basically the oxygen because of its covalent, it's forming 2 bonds, so that's going to be averaged out. That does not affect the degree of unsaturation. So C4H8, if it was, this would have got degree of unsaturation 1. That's what we are saying. This compound also has got degree of unsaturation as 1. We then will be finding the number of possible functional groups. So once we know the formula, what are the heteroatoms other than the carbon and hydrogen, we can be seeing the possibility of the functional groups. So we are having two set of informations. We are having one oxygen atom and we are having 1 degree of unsaturation. So the possible outcome from this can be, we can be having C double bond O, we can be having C double bond C with enol, we can be having unsaturated ethers, cyclic alcohols, cyclic ethers. Not many of the possibilities are there. So in the questions, we have been asked about the first possibility, that is carbonyl compound. We have been asked about enols, and we have been asked about the cyclic ethers. So we will not be counting about the cyclic alcohols or the unsaturated alcohols, which is enols basically. Those we are counting. We'll be seeing how we are going ahead one by one. So what we should be doing for each functional group, like say we know some of the aldehydic functional groups and some of the ketonic functional groups are present, some of the alcohols are going to be present. So for each of these groups individually, we will be following the next step. What the next step is, suppose we are trying to write all possible carbonyl compounds, then what we should do, we'll draw all possible chains. So in the 4 carbons, there are 2 types of chains possible. Number 1, all 4 carbons arranged in a straight line, and number 2, there can be 1 methyl branching as well. So once we are done with that, drawing all possible chain isomers, now we'll start putting the functional groups or the substituents whichever are available. So in the aldehydes and ketones, there is nothing other than the function, keeping the functional group, that's the double bond O, onto different groups. So we'll be getting all the possibilities for the aldehyde ketones. And the same thing should be repeated for enols and for the unsaturated ethers and unsaturated and the cyclic alcohols as well as cyclic ethers. So OH group is there, then it can be replaced by OR group when we are going for ethers, and then we can be seeing the possibility of how these different substituents can be changed, like double bonds position can be changed, as well as the position of methyl in the carbon chain can also be changed. So having that done, now we should be keeping one thing in mind, that we should not be repeating the isomers over and again, and writing IUPAC names can be one of the very much good clue, so that we are not repeating any of these, because same analytical compounds, if you have repeated one, you'll be finding that same name to be written more than one. So IUPAC names are going to be one good cross-checking mechanism. Writing IUPAC name can be giving us one very much clear idea whether we have repeated something or everything is well in place. Okay, then the next step would be, actually this does not cover our metamers. So whenever we are having the heteroatoms present, polyvalent heteroatoms present in our carbon chain, it can be the case of oxygen, nitrogen, organic compound, I think sulfur sometimes we can be finding. So whenever these cases are there, we should be thinking of the possible metamers, where if there are 2 alkyl chains onto the left and onto the right, these possibilities of chain should be exchanged, and we can be writing more than one possible metamers. That should also be done wherever possible. Like in the case of unsaturated ethers, we'll be doing so. In one of the cases, we'll be keeping 2 and 2 carbons on both the sides, and in another case, we'll be keeping 3 versus 1 carbon on the 2 sides of the ether functional group. Not ether, actually not as a functional group as such. In the nomenclature, we are not keeping it as a functional group, but when we are talking about their chemical behaviors, chemical reactions, we may be considering as ether as one of the functional group. So now after this point, we'll be checking each and every single compound for the possibility of the geometrical isomerism. If we have the possibility of geometrical isomerism, we can be finding some of the compound can be existing in diastereomeric forms, and after doing so, we should be checking for the possibility of the optical isomers. Like we should be checking whether there is a plane of symmetry present, center of symmetry or alternate axis of symmetry present. If it was, our compound is going to be optically inactive. Otherwise, there would be some isomers, some enantiomers or the diastereomers of that compound possible if that compound is asymmetric. So that is the algorithm. What if we follow, we can write all possible isomers in all possible cases. Okay, so let us apply to this what algorithm we are suggesting, how this can be applied to our given problem. So first of all, we are thinking about the number of carbonyl compounds which can be there. So first of all, we are trying to write aldehydes, and see in aldehydes we have got two possibilities. Number one, we have chosen the aldehyde group first, CHO group is there. Now we are thinking of possibility of carbon chains. There can be a 4 carbon chains in a straight line, something like this. This is 1, 2, 3, and 4. And this is another possibility where all the carbons are not present in a carbon chain. One carbon is going to be present as the side chain as well. Now, aldehydes, only these two possibilities are there. Then we are going for the next functional group, which can be ketone for C double bond O. And in ketone, we now realize that there's only one possibility where there can be C double bond O either at carbon number 2 from the left or at carbon number 2 from the right. This is going to be identical. So there is only one ketone and only 3 aldehydes possible. That was the X was equal to 3. Unsaturated alcohol, that number was found to be Y in our problem. So here we go. What we are trying to do is we are trying to keep the carbon chain in one fashion. So first of all, we are talking about but 1-enol. So we have chosen a carbon chain where double bond is present on one of the terminus, and then we are putting the positions of OH onto different possible carbons. So out of these all but 1-enes, we are putting the all on position number 1, on position number 2, on position number 3, and on position number 4. Because we are not considering the all possible isomers, so basically we are ignoring the stereoisomers. Otherwise, the compound number, this one, let us say compound number A, would be having this double bond as cis and trans or E and Z. Compound number 2, not possible. Compound number 3, there is a chiral carbon because there is a hydrogen present as well. And compound number 4, no stereoisomerism is possible. So if we are counting stereoisomers as well, compound number A and compound number C are going to have stereoisomers as well. That was about but 1-enol, where double bond was present on carbon number 1. Now if we are going for the but 2-enols, where double bond is going to be present in carbon number 2, we are having much more possibilities of the stereoisomerism, but we are not going for the stereoisomers right now. We are just counting all possible structural isomers. So in this but 2-enol, double bond is in carbon number 2. Now alcoholic group can be on carbon number 1 or alcoholic group can be on carbon number 2. So 2 but 2-enols are possible, and also there will be some methyl propanol possible. So if you are keeping now 3 carbon chain, so earlier 2 examples we have kept 4 carbon chain like this. In this example we are keeping a 3 carbon chain and there is a branching of methyl. Now in this earlier case, you had 2 possibilities of keeping double bond in the terminus or in the middle. Right now you keep double bond wherever possible. This does not affect. This is going to be exactly the same. Now over here we can change the position of OH. We can keep the OH group on carbon number 1, or we can keep it on carbon number 3. Cannot keep it on carbon number 2 because carbon cannot be pentavalent. So the total number of compounds for the unsaturated alcohols are going to be 8. 4 of these but 1-enols, 2 of these but 2-enols, and 2 of these methyl propanol. So Y was equal to 8. Now coming to the Z, we are talking about Z1 first, which is aliphatic ethers. So you remember when we were talking about ethers, there is going to be one possibility of metamers where we can be swapping the alkyl groups. First of all, we are adding methoxypropenes. So in methoxypropenes, what we have done, we have kept 3 carbon on one side, then there is oxygen, and then is 1 carbon onto the other side. Later, what we'll be doing, 2 carbon on one side, oxygen, and then 2 carbon onto the other side. That will be ethoxyethanes. Okay, so this is the double bond on the carbon number 1. That is going to be 1 methoxypropene. This is where double bond is on carbon number 2. That is going to be our 2 methoxypropene, like this. And there is another possibility where this is going to be, sorry, this is carbon number 1, carbon number 2, carbon number 3. So 1 methoxypropene, sorry, this numbering we have done wrong. 1 methoxypropene, 2 methoxypropene, and 3 methoxypropene. These 3 methoxypropenes were possible. Because double bond is given priority, this is considered as a functional group. So this is first compound 1 methoxypropene, second compound 3 methoxypropene, third compound 2 methoxypropene. That is how these compounds would be named. And these are 3 basically aliphatic ethers in the methoxypropene and 1 ether in the ethoxyethene. Sorry, this should be ethoxyethane. So this is the next compound, which is basically 2 plus 2 carbon, only one possibility. We cannot change anything. We cannot change the position of double bond. We cannot change the number of carbons as well. That is for Z1. Z1 was 4. Coming to Z2, alicyclic ethers, where we'll be seeing some cyclic change present and oxygen would be present somewhere in our compound. It can be the part of that cyclic ring, that oxygen, or it can be present outside of that ring as well, because oxygen cannot be trivalent. It cannot be present at the junction where the branching of the alkyl group can be there. If it was nitrogen, that could have been one possibility. So starting with the options, first one we are having like alicyclic ether. The first possibility is a 5-membered ring with 1 oxygen. We call this compound as tetrahydrofuran, THF. Now next possibility is pretty much straightforward. We are going to have the 4-membered ring where methoxy group can be present onto the alpha carbon of oxygen or onto the beta carbon of oxygen. Although we can be realizing later that this compound is going to have a plane of symmetry over here, and this compound is having no plane of symmetry. So this one is going to be optically active. This is going to have stereoisomer. The second compound is not going to have any stereoisomers. Then we have got 3-membered ring, many possibilities arising over here, because you have a possibility of keeping ethyl group onto this 3-membered ring thing. You can keep 2 methyls, both the methyls at the same carbon or both the methyls onto the different carbon. And then there is one possibility where the oxygen is present outside of this 3-membered ring, and we are getting this methoxycyclopropane. So alicyclic ethers, we had 7. 1, 2, 3, 4, 5, 6, 7. We had got 7 such alicyclic ethers present. This is how we can be counting all possible isomers. Now we have not done the stereoisomers. So here we have put them all together, and here we can see which all of them can have the stereoisomers as well. If stereoisomers are not included, if they are not being counted, then these are all possible isomers which we were asked in the given question. So I will be mentioning over here what are all those where stereoisomers are possible and how many of those are possible. So I'll be writing, say, +1 where only 1 extra isomer is present. I'll be writing +2 if there are 2 extra isomer other than the one given there is present. So in the carbonyls, there are no stereoisomers possible. In this one, this is the stereo center, so this is going to have 1 extra carbon. Basically, cis and trans can be possible in this case. Same thing happens with this compound. This is also stereo center. This is also going to have +1 extra compound, which is going to be the geometrical isomer of this compound. This compound is again going to have the stereocenter. So here also we are going to have +1. This compound is having 2-methyl, not a stereocenter. This compound is having 1 hydrogen present over here. So this is going to be the stereocenter for the optical isomerism, +1 for this. And here in this case, no isomers are known. This compound, because 2 methyls are coming, no stereoisomers. This compound, again, no stereoisomers because you cannot have cis trans, you cannot have optical isomerism. Coming to the ethers, this carbon is again going to be the chiral center because there can be hydrogen onto the opposite side as we are seeing over here. They can be onto the same side as well. So we are adding +1 here. And in this case, again, nothing is possible because this is the terminal double bond and there is no chiral carbon. Same thing arises here. No such possibility of the stereoisomerism. This compound, again, no stereoisomers, 5-member ring in ethers, 5-member ring, no stereoisomer. This compound we're talking of, this compound is because it's having a plane of symmetry. This is going to be optically inactive. No another isomer is possible in this particular case. But over here, because you are having 1 hydrogen present, this is going to have optical isomer. This is going to be 1 more such compound possible. In 3-member ring, just like the case of this compound, which is alpha-methyl cyclobutane, this compound is also going to have the very much similar situation. This is going to have one extra isomer, which is basically its enantiomer. This compound, 1,1-dimethyl 1,1-dimethyl ethylene epoxide or oxidant, we can say this is also not going to have any isomer because there is no chiral carbon present. This compound, which is having 1,2-dimethyl epoxide, this is going to have this carbon as chiral and this carbon also as chiral. This compound is going to have 2 more stereoisomers. Other than that, the idea is if this compound can exist in cis and trans configurations, like the methyl groups, these can be cis or trans to each other. When they are cis to each other, that is meso compound, no enantiomer for that is possible. But when that one is trans, then we are having stereoisomers possible because that will be having enantiomeric modifications. The last compound, it does not have any optical isomer or geometrical isomer, although there is 1 hydrogen present over here, but this chain going along this line from this one and this one, they are going to be exactly the same. So this compound is not going to have any other stereoisomers. So if you had to count all possible isomers other than those what we have seen earlier, these are the extra compounds which we are going to have. 1 here, 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 and 2 over here. This is the all possible isomers. I hope you can do the questions on the basis of discussion done over here. For any such question where they are asking the count the number of stereoisomer or count the number of total possible isomers. That's all for now in this video. Thank you. Bye bye. See you next time very soon.